You know, when we think of calculus, we usually think about the mathematics of change, right? Slopes, curves, all that good stuff. But if you ever stop to ask, what is calculus itself actually built from? Well, today, let's put the calculator away. We are not going to be solving problems. Instead, we're going to be architects. We're going to look at the actual plans, the blueprint that makes calculus possible, and it's all drawn directly from the foundational text, Jiaetic 1a.
So here's the big question we're tackling. If calculus is this magnificent cathedral of logic, what are the stones? What's the mortar? What are the design principles that hold the entire thing together? What is the fundamental blueprint?
Right. Just like any huge construction project, you gotta start with the plan. So to really understand calculus, we have to start right there, at the very beginning, by looking at the foundational concepts that everything else is built on.
Okay, so first things first, we need our raw materials. And in the world of mathematics, the most basic material, the very alphabet we use to write every single equation and every proof, is the idea of a set.
And what's so cool about this is how beautifully simple it is. A set, or taphap as our source text calls it, is really just a collection of distinct things. That's it. It could be a set of numbers, a set of letters, even a set of cats. And believe it or not, this super simple idea, it's the starting block for, well, for everything.
And hey, you're already familiar with some of the most important sets out there, even if you don't think about them that way. They're like Russian nesting dolls. We start with the natural numbers, the ones we count with. They sit inside the set of integers, which brings in negatives and zero. And those are part of the rational numbers, fractions. And all of that is contained inside the giant set of real numbers. These are our primary building blocks.
Okay, so we have these bags of stuff, our sets. What can we do with them? Well, we can combine them in a couple of really important ways. We can take their union, which is kind of like dumping everything from two bags into one big pile. Or we can find their intersection, which is where we only keep the things that were in both bags to begin with. Simple moves, but they are incredibly powerful.
Now this is a really clever way to combine sets. It's called the Cartesian product. You're basically pairing up every single element from one set with every single element from another. And seriously, if you've ever plotted an XY point on a graph, yep, you've used a Cartesian product. You were doing it all along. You're just creating a new set of ordered pairs.
All right, so we've got our materials, these sets. Now where are we going to build this thing? We need a construction site. We need that perfect, solid ground where we can start building. And for calculus, that site is the set of real numbers.
But here's the thing, and this is super important. Not all number lines are created equal. If we tried to build calculus using only the rational numbers, all the fractions, our number line would actually be filled with these tiny invisible holes. It'd be like a road full of potholes. The real number line, on the other hand, is perfect. It's continuous. It's a solid foundation with no gaps at all.
So that kind of makes you wonder, right? What exactly is filling in those gaps between all the fractions? And maybe more importantly, why does it matter so much? Why is having a perfectly solid line so absolutely critical for calculus?
Well, the answer is this absolute powerhouse of an idea called the completeness axiom. Now, I know, that sounds super technical. But its job is actually pretty straightforward. It's the rule that guarantees there are no holes in the real number line. It basically says that if you grab any chunk of the line, and that chunk has a ceiling, then it also has a perfectly defined, precise upper edge. Let's just call it the no gaps guarantee. That's all you really need to remember. This is the property that makes the real number line a truly solid foundation, one that's strong enough to support the entire massive structure of calculus, which is all about smoothness and continuity.
Okay, let's make this real. Take a look at this number, a classic example, the square root of 2. This number is a perfect illustration of one of those gaps we were just talking about.
So the square root of 2, there's just no way to write it as a simple fraction. It doesn't work. It falls right into one of those holes on the rational number line. But it absolutely exists on the real number line. The completeness axiom guarantees it has a home. And for calculus, which is all about these infinitesimally smooth changes, those gaps are a complete deal breaker. We need a solid path to work on.
Okay, quick recap. We've got our materials, sets. We've got our perfect construction site, the real numbers. What's next? Well, now we need the machinery, the tools that are going to operate on our materials. In math, we call these tools mappings, or as you probably know them, functions.
So first up, we have what's called an injective mapping, or dönang. Think of this as our one-to-one machine. It's incredibly precise. It's like a perfect code where every single input goes to a totally unique output. No two inputs ever end up in the same spot. Then we've got the subjective mapping, or duanang. This one is our onto machine. This machine is all about coverage. It guarantees that every single possible output you could want is hit at least once. Nothing in the target zone gets missed.
So what happens when you get a mapping that does both? One that's one-to-one and onto. You get a bijective mapping, or song-ang. And this, my friends, is the gold standard. It's a perfect pairing, a flawless one-to-one correspondence. Every input has its own unique output, and every output is accounted for. This is crucial for things like inverse functions, which are essential tools in the calculus toolbox.
All right, let's zoom out and look at the whole blueprint we've just laid out. We've seen how these three really fundamental, kind of abstract pieces, sets, the real numbers, and mappings, all fit together perfectly.
We started with our basic alphabet, sets. Then, we engineered the perfect gap-free construction site with the real numbers and their no-gaps guarantee. And finally, we built the machinery, the mappings, to act on them. With this foundation firmly in place, we are finally ready to begin construction, to build the magnificent structure of calculus itself.
And here's the big takeaway from all of this. These foundational ideas, they aren't just abstract rules you have to memorize for a math class. No way. They are the carefully designed, elegant, and absolutely essential principles that make everything else possible. They're what let us do all the amazing things calculus does, like figuring out the slope of a wild curve, or even calculating the volume of a planet. It's that fundamental. And that leaves us with one final, really exciting thought. Now that we have the complete blueprint, and the foundation is rock solid, what can't we build?